Welcome to the second half of section 7.3. I'm going to start with a quick review and then we're going to jump into calculus. So let's plot these points. If we want to plot r theta equals 2 comma 5 pi over 6, then we go to the angle 5 pi over 6, which is over here, and we go 2 units out. 1, 2. That's point A. For negative r, well, again, we go to the angle first, so I'm going to go to the angle 5 pi over 6. And then instead of going 2 units out, since r is negative, I'm going to go 2 units in the opposite direction. 1, 2. So that's point B. Okay, and let's do a conversion. We're going to convert from rectangular to polar. And here are my conversion equations for our easy reference. And I've started us out. R squared is x squared plus y squared. That gives us 16. So r is plus or minus 4. And then tangent theta is root 3. So that tells me that theta, I want two angles between 0 and 2 pi. Theta is going to be pi over 3 or 4 pi over 3. All right, now I need to match the r with the theta. So this point is in quadrant 3. There's my point, somewhere in quadrant 3. If I choose the positive value of r, which is 4, then I want the angle in quadrant 3. I want 4 pi over 3. If I choose the negative value of r, I want the angle in the opposite quadrant, which is pi over 3. Piece of cake. Okay, sketching by hand. With technology nowadays, you're really not going to need to do this, but if you are stranded on a desert island, I would want you to know how to sketch a polar curve by hand if you had to. So you can just do this naive method of plotting points. We want to sketch r equals 4 sine theta. We'll see in a minute that this is a circle. But if I choose some values of theta, let's see what r is. If theta is 0, r is 4 times sine of 0, which is 0. Well, that tells me that 0, 0 is on the plot, on the curve. So the origin is on the curve. And then if theta is pi over 4, r is 4 times sine of pi over 4, which is 1 over root 2, which gives me 2 root 2. So to plot that point, r comma theta equals 2 root 2 comma pi over 4. I go to pi over 4 first. Here's my angle, and I go 2 root 2 units out. Maybe there. All right, pi over 2, r is going to be 4. So I go to the angle pi over 2 and go 4 units out. I don't know how far that is, but I know it's more than 2 root 2. And then when theta is 3 pi over 4, r is again back to 2 root 2. So that would be here. And then when theta is pi, r is back to 0. So I've come full circle, so to speak. Now, this could be a baseball diamond, but I know it's a circle, so I'm going to connect those points with a, well, okay. It's somewhat a circle. Okay, so that's how you would sketch by hand. Desmos is awesome for graphing polar curves. So let me just show you, if you wanted to graph 1 plus cos theta, how you would do it on Desmos. You just go r equals 1 plus cos and type in the word theta. And if you use r and theta, Desmos automatically knows that you want polar coordinates, and it knows it's going to graph a polar curve. Just like when you use t, it knows you want parametric. So here's my curve. It's called a cardioid, and that was very easy. Now, the default interval on theta is 0 to 2 pi, but if you weren't sure you were getting the whole curve, you could always change that to 4 pi. It turns out that we were getting the whole curve, but maybe 2 pi was too much. Maybe you would have gotten it from 0 to pi. You could try that. Nope, we only get half of it. So we really did need 0 to 2 pi. Okay, special polar graphs. So you don't have to memorize these. They're just for your information. You do have to know some of them. So here are the cardioids and the limacons, the roses, and down here the lemniscates. I want you to know about the circles. And so we just graphed r equals 4 sine theta, and it looked a lot like this one, r equals 2 sine theta. R equals a sine theta will always look like it will lie above the x-axis or below if a is negative, above if a is positive, and it will have diameter a. Cosines go the other way. They lie either to the right or the left of the y-axis depending on whether a is positive or negative. And the interesting thing is all of those circles have period pi. You get the whole circle from going from 0 to pi. And we saw that when we graphed this circle up here. I only went from 0 to pi and I got the whole circle. Whereas your typical circle, r equals a, that we talked about last time, this has period 2 pi. Because in order to get this whole circle, I have to start at theta equals 0, and I have to go all the way around to get the whole circle. All right, so now let's do some calculus. Slopes and tangents. How to find the slope of a polar graph. So we're going to use what we already know. We know the parametric slope formula. We know dy dx is dy dt over dx dt, if t is the parameter. Well, the only thing different now is we're changing the parameter from t to theta. So we're going to call the parameter theta, and the way we'll parameterize our curve is x is r cos theta, y is r sine theta. So that's step one. Write your curve parametrically. Step two, just plug and play. Find dy dx. Then if you want to go further and find an actual tangent line, you're going to take this dy dx and evaluate it at the theta in question. Let's say you want to be at a specific spot, like pi over 3. Then you would evaluate this general formula at pi over 3 and get a number. That would be the slope. You'd need your x naught, y naught. That would be a point on the line. And to get x naught, y naught, you're going to plug pi over 3 into your formulas for x and y, and then use point slope. So if you're confused, that's okay. We're going to do an example. We're looking at the cardioid, r equals 1 minus sine theta, and we want to find the slope at theta equals pi. So step one, I want to parameterize the curve. So x is r cosine theta, which is r is 1 minus sine theta. So that's times cos theta. And we're going to have to expand that out. That's cos theta minus sine theta cosine theta. Y is r sine theta, which is 1 minus sine theta times sine theta, which is sine theta minus sine squared theta. Okay, step two, find dy dx. dy dx is dy d theta over dx d theta. I always write down a formula if I'm going to use it. dy d theta, so here's why. Take the derivative with respect to theta, we get cos theta minus, have to use the chain rule, bring a 2 down, sine theta, and then multiply by the derivative of the inside, which is cosine theta, over, now I want dx d theta, x is up here, so the derivative, it's kind of messy, the derivative with respect to theta is negative sine theta minus, now I need the product rule, and so I'm going to use brackets so I remember to distribute that minus. The derivative of sine theta is cosine theta, so I'll get cosine squared theta, plus the derivative of cosine is negative sine, so actually that'll be minus sine squared theta. All right, and then I'll just distribute that minus downstairs to clean up, and that's about all I can do. Cos theta minus 2 sine theta cos theta over negative sine theta minus cosine squared theta plus sine squared theta. All right, that's the slope at any value of theta. I want the slope at theta equal pi. So at theta equals pi, dy dx is cosine pi minus 2 sine pi cosine pi over negative sine pi, which of course is 0, minus cosine squared pi. I'm going to write that as cosine of pi all squared, just so I know where my square is, and then sine pi all squared. All right, so on top, I just get negative 1, because this part's 0, because sine of pi is 0. Then downstairs, I get 0 minus Negative 1 squared is positive 1. So 0 minus 1 and then minus 0. So I'm getting negative 1 over negative 1, which is positive 1. If I lost you, pause the video and make sure you can follow that. So that's my slope. All right, find an equation of the tangent line at that same point at theta equals pi. Well, so what we've done is we've done steps 1 and 2. We found a general formula for the slope. That's in step 2. And then we actually did this step with our theta naught equal to pi. We found the slope at a certain point, and that was 1. Now we need our x naught, y naught. That's going to be x at pi, comma, y at pi. All right, well, how do you figure that out? You go up here. This is x, and this is y. So you're going to put pi in for theta to get your x and y coordinates. So x of pi, we can see, is negative 1. And y of pi, we can see, is 0. Now, point slope. We've got our m from the previous step. That was m equal 1. And we've got our x naught, y naught. So point slope, y minus 0 is m, which is 1, times x minus negative 1 is plus 1. Y equals x plus 1. Let's see if that seems reasonable. Let's go up here to our cardioid. X naught, y naught was negative 1, 0. That was here. And we're finding the equation of the tangent line there. And we saw that that was y equals x plus 1. It certainly seems reasonable. It's got a positive slope, positive y-intercept. So I'm happy with that. Let's take this a little further. Where between negative pi over 4 and pi over 4 does the curve have a tangent that's horizontal and or vertical? Not and or, but or vertical. Pi over 4 is about here, and negative pi over 4 is about here. So I'm looking at that interval there. It looks like I do have a horizontal tangent about there, and it looks like I have a vertical tangent about there. But let's check that out. Recall from the previous page, so I just copied and paste, this was our slope. When we found the slope formula, dy dx, this is what we got. So for the first part, horizontal, we want to know when m is 0. Horizontal lines have slope 0. So m equals 0 if and only if the top of this fraction is 0. Fraction 0 only when the numerator is 0. So I set the numerator equal to 0. Factor a cosine out. 1 minus 2 sine theta is 0. So cos theta is 0, or sine theta is a half. Now remember, we're only going from negative pi over 4 to pi over 4. So cosine is never 0 in that interval. Sine is equal to half at theta equals pi over 6. All right, now we need x and y. So we need x at pi over 6, comma y at pi over 6. Now I'm going to leave it to you to verify that that's actually going to give us root 3 over 4, comma 1/4. How are you going to verify that? I've got my formulas for x and y on the previous page. Here they are. This is x, and this is y. So you're going to put pi over 6 in for theta into each formula and verify that this is indeed the point you're getting. All right, now let's do the vertical. M is undefined if and only if the denominator of that fraction is 0. So negative sine theta minus cosine squared theta plus sine squared theta is 0. All right, and I wanted to solve that with you. I want to get everything in terms of sine. So I'm going to change these cosines over with the Pythagorean identity. This is negative sine theta minus, write cosine squared as 1 minus sine squared plus sine squared theta equals 0. And if I clean that up, I get 2 sine squared theta minus sine theta minus 1 is 0. I want to factor that. That factors as 2 sine theta plus 1 times sine theta minus 1, and that equals 0. I'm running out of real estate, so I'm going to come up here. So that tells me that either sine theta is -1/2 or sine theta is 1. Now again, remember that we're only going from -π/4 to π/4. So sine theta equal 1 is not going to have any solutions, but we will get theta equals -π/6 for this equation. And again, I'm going to leave you some work. Verify that x of -π/6, comma y of -π/6 is 3√3/4, comma -3/4. All right, and I'm going to show you that on Desmos. There's our cardioid, and here's the point, √3/4, comma 1/4, and we see that we do have a horizontal tangent line there. And then this is the point, the second point we found, where we indeed have a vertical tangent line. Okay, so this last example, I'm going to just walk you through parts of the solution, which I already have written down. It's the questions are almost identical to the ones we just answered. It's just a different curve. So in this case, we have a circle, r equals 3 sine theta, and we want to find the slope at 2π/3 and a Cartesian equation of the tangent line there. And then where between 0 and pi does the curve have a horizontal tangent / a vertical tangent? So step 1, x is r cos theta, r is 3 sine theta. So I filled that in. Y is r sine theta, so that simplifies to 3 sine squared theta. Then dy dx is dy d theta over dx d theta. So we take the derivative of y using the chain rule. You can verify that you get this. And then for dx d theta, we use the product rule. You can verify you get this. Then I went ahead and I plugged in 2π/3 for theta to get the slope of my tangent line. And you can check my arithmetic, but we're going to get √3. And there are x0, y0. Now that's going to be x at 2π/3, y at 2π/3. And so you're going to take 2π/3 and plug it into this equation for x and this one for y, and you should get -√3 times 3/4 and 9/4. So that's going to be, let's say, probably about there. And your slope is √3, so the tangent line looks something like that. And then the part I didn't do yet is horizontal / vertical tangent. So let's do horizontal first. Looks to me like we're going to find 2 spots where there's a horizontal tangent. If m is 0, we're going to set the numerator of this is a real mess, the numerator up here equal to 0. So m is 0 if and only if 6 sine theta cosine theta is 0. Well, that's sine theta is 0 or cosine theta is 0. Now we're going from 0 to pi. Sine theta is 0 at 0. We're not including pi because I left the endpoint off. So just from 0 to pi, not including pi. And then cos theta is going to be 0 at pi/2. So we're going to get two values of theta. We're going to need x at 0, y at 0, and we're going to need x at pi/2, y at pi/2. So x at 0, y at 0, up here is our xy equations. You can see we're getting the origin, 0, 0. And if we put pi/2 into those two equations, x will still be 0, but y will be 3. So we are down here, and we are up here at the top of the circle. And you can imagine we're also going to get two values where slope is undefined, corresponding to these 2 points. So we'll do that now. M undefined, if and only if the denominator is 0, and the denominator I speak of is this one, 3 cosine squared minus 3 sine squared. That should be 0. So move the 3 sine squared to the other side and divide both sides by 3. Cosine squared theta is sine squared theta. So cos theta is plus or minus sine theta. All right, so that's going to give us theta equal, well, they're equal at pi over 4, and they're opposites. One is negative and one is positive at 3 pi over 4. And we're going to stop there because we're only going from 0 to pi. And I'll leave it to you to verify that x of pi over 4, y of pi over 4 is 3/2, 3/2, and x at 3 pi over 4, a lot of parentheses there, y at 3 pi over 4 is negative 3/2, 3/2. All right, and that is the end of this section.